wondered why a bird can sit on a power line without getting a shock? You may even wonder why the sign warns of danger. You too could sit on power lines if you could find a safe way of landing on them and getting off safely. If perchance you decided to climb down the supporting tower, the instant you touch the tower, you'll wish you hadn't. You have probably experienced some of the scientific principles involved in the fate of our unfortunate parachutist, but in a less dramatic way. If, while standing on a carpet on a cold winter day, you were to remove your sweater, you wouldn't feel a thing. But your hair would indicate that you were carrying an electrostatic charge. We can explain electrostatic effects by assuming that charge is either positive or negative. If you now touch a water tap, you may get a shock as the charge suddenly flows out of your body, and in so doing, discharges or neutralizes your body. Since metals allow charge to flow through them easily, they are called conductors. However, charge cannot leave your body by flowing through the carpet. Materials like carpets are called insulators, since they do not permit charge to flow easily. Why do materials differ in this way? We believe that all substances consist of tiny particles called atoms. Our current model of the atom assumes that it is mostly empty space. And in a tiny volume called the nucleus, over 99% of the mass of the atom is concentrated. Further evidence suggests that the nucleus is made up of particles called protons, which are positively charged, and neutrons, which are neutral in charge. Neutrons and protons are almost identical in mass. In the space surrounding the nucleus are tiny negatively charged particles called electrons. The attraction between the negatively charged electrons and the positively charged nucleus keeps the electrons in the vicinity of the nucleus as they circle it. It takes 1,837 electrons to equal the mass of one proton. But the charge on a single electron exactly balances the positive charge on a proton. Electrons, which are farther away from the nucleus, experience a smaller force of attraction than those which are closer to it. These outer electrons can be removed with relative ease. The nucleus, on the other hand, is like a well-built fortress. And inside, the protons and neutrons are the prisoners. Even disruptions, like explosions and high temperatures, leave the nucleus intact. This fortress-like character makes it impossible for charges to enter and leave at will. With this background, let's have another look at insulators and conductors. Remember our atomic model. A metal conductor is largely empty space. The nucleus of each copper atom contains 29 protons and 34 neutrons, and is surrounded by enough electrons to balance its positive charge. The outermost electron is very loosely held. It can therefore drift away until it comes under the influence of another nucleus. The atom now has one less electron than it has protons. Consequently, it is no longer neutral, but it has a positive charge. Atoms become ions when they become charged by gaining or losing electrons. Since all copper atoms have a loosely held outer electron, we can visualize a metal conductor like this. The nucleus and electrons near it are positive ions. Spread throughout the network of ions are loosely held electrons. Suppose we watch one of the electrons. Over a period of time, it appears to move throughout the volume of the metal. If we place a positive charge at one end of the metal object and a negative charge at the other end, the electron will be attracted to the positive charge and repelled by the negative charge. Accordingly, as the electron follows its random path, it gradually drifts towards the positive charge. The charges on either end also affect the nuclei in the metal. Remember, the protons making up the nucleus are not able to escape from it. In solids, the nucleus and the ion of which it is a part will only vibrate. The reason for this immobility is because the ions are joined together in a network. Although each nucleus will be attracted to the negative charge and repelled by the positive charge, individual nuclei and ions cannot move in response to the electrostatic attraction and repulsion that they experience. In solids, a transfer of charge can only be accomplished by electrons moving from one point to another. Why then do insulators not allow for the same transfer of charge? Materials like carpets are complex substances composed of many different types of atoms. We will show these atoms as different colors. In this case, the outer electrons of most atoms are involved in chemical bonds with other atoms. As a result, these electrons do not have the freedom of movement found in metals. When opposite charges are placed at the ends of the carpet, little, if any, movement of electrons occurs. Not all insulators are as complex as carpets. Sulfur atoms, for example, will form bonds with adjacent sulfur atoms. Again, we have a substance within which electrons are not free to move. Opposite charges placed at the ends of a chunk of sulfur do not result in a flow of charge. If you become charged by taking off a sweater, we now know that you can discharge by touching a conductor, because a conductor allows excess electrons to flow from your body. It would seem that our intrepid parachutist touched a conductor when he reached for the power pole. But what about the power line itself? We know that electricity is flowing in the wire, so it's probably a conductor. Why then can a bird, or even you or I, sit on a wire and not get a shock? You may think that the wire is insulated, but actually our bold pair could sit on a bare wire and not get a shock. Obviously, we have some answers, but not all. Maybe we should next find out how we get charged in the first place. When you carry an electrostatic charge and touch a metal object, you sometimes get a shock. The shock is caused by the sudden flow of electrons between your body and a conductor, in this case, the metal tap. The atoms which make up a conductor are thought to consist of positive ions, with a number of loosely held electrons, which move at random, drifting towards one nucleus and then another. Opposite charges placed at each end of the metal cause these electrons to drift from the negative end to the positive end as they proceed in their random motion. Ions also experience forces of repulsion and attraction. But if the material is a solid, they will not be able to move about freely. Transfer of a charge through a solid can only be accomplished by the motion of electrons. But why does taking off a sweater result in electrostatic charges? Before you get dressed, both the cotton shirt and the wool sweater are electrically neutral. When the wool and the cotton come in close contact, however, things begin to happen. As a group, the atoms making up the cotton fabric have a stronger attraction for electrons than the atoms making up the wool. As a result, some electrons transfer from the wool to the cotton. When the first electron transfers to the cotton, the overall charge of the cotton changes from neutral to -1. But the charge on the wool has changed as well. It has one more positive than negative, resulting in an overall charge of +1. As more and more electrons are transferred from the wool to the cotton becomes more and more negatively charged. And the wool becomes more and more positively charged. There's a limit, however, to the number of electrons which can be transferred before the positive charge on the wool begins to attract some of them back. Both the cotton shirt and the wool sweater consist of billions and billions of atoms. So instead of trying to show all the charges, we'll just show a representative sample on each garment. When the two materials come in close contact, we can show the charge transfer from the wool to the cotton in this way. The cotton, with its excess of electrons, becomes negatively charged. The wool, with its deficiency of electrons, becomes positively charged. Note that during the process, the positive charges never move. Both the cotton and the wool are good insulators, so the charge transfer is limited to where there is contact between the two. If you are wearing a negatively charged shirt, how can you neutralize it? Easy. Simply touch a metal water tap. The excess electrons will transfer from your finger to the tap until the negative charge on your shirt balances the positive charge. The pipe to which the tap is attached runs deep into the ground. This connects to the earth, which is neutral in charge. Because of its vast size, the addition of small amounts of charge, or its removal, does not significantly affect the Earth's overall charge. The process of connecting something to the Earth by means of a conductor is called grounding. So far, we have shown what happens when we carry a negative charge. But what happens when we carry a positive charge? Suppose you decide to wear a rubber raincoat over your cotton shirt. Again, the initial electrical charge on both garments would be neutral. Now, rubber has a stronger attraction for electrons than cotton. As a result, the electrons transfer from the shirt onto the rubber raincoat. The raincoat now has a negative charge, and the cotton shirt a positive charge. If we remove the raincoat and wear only the positively charged shirt, look what happens when we touch the water tap. As usual, there's a spark. This time, electrons flow from the Earth into the arm, and in so doing, neutralize or discharge the shirt. Grounding, the process where we connect a charged object to the Earth, will discharge that object, whether it is positively charged or negatively charged. How do we know when an object is charged? The metal leaf electroscope can detect charge, even in very small amounts. It consists of a metal shaft, which has a knob on one end and very delicate metal leaves on the other. The shaft is insulated from the container which encloses it. When the knob is touched by a charged object, look what happens. We can explain this phenomenon by applying some of the theory we have just established. The initial charge on the electroscope is neutral. When the electroscope knob is touched by a negatively charged rod, a number of electrons jump onto the neutral knob. We call this process charging by contact. Remember that each electron repels every other electron, and the repulsive force they exert on each other will cause them to move as far apart as possible. Since the electroscope is metal, the electrons are not confined to the knob, but spread themselves uniformly throughout the entire electroscope. Because the electroscope now has a negative charge, the leaves will repel each other and diverge. If we touch the electroscope with a positively charged rod, the result will be the same. This time, some electrons transfer from the knob to the positively charged rod. The resulting shortage of electrons leaves the electroscope with an overall positive charge, and accordingly, the leaves will again repel each other. Charging by contact isn't the only way to charge an electroscope. Next program, we'll demonstrate a technique in which the charging rod never touches the electroscope. One way to acquire an electrostatic charge is to come in close contact with another object that consists of different material. Cotton, for example, has greater attraction for electrons than wool. Therefore, when these materials come in close contact with each other, electrons transfer from wool to cotton. The cotton now has an overall negative charge, and the wool an overall positive charge. Their opposite charges account for the static cling when you attempt to separate them. The easiest way to neutralize a charged object is to connect it to the Earth with a good conductor called a ground. If the object is negatively charged, the excess electrons flow into the ground until it is neutral. If it is positively charged, electrons flow from the ground into the object until once again it is neutralized. Close contact between two neutral objects is not the only way to acquire an electrostatic charge. If a neutral object is touched by a charged one, there will be a transfer of charge as electrons flow from the charged object to the neutral one. And how do we detect charge? A metal leaf electroscope can be used to detect relatively small quantities of charge. When it's touched by a positively charged rod, electrons move from the electroscope onto the rod, leaving an excess of positive charge. As a result, the metal leaves repel each other, evidence that the electroscope is charged. Have you ever noticed that an electroscope, when approached by a charged rod, seems to anticipate what is about to happen? The leaves diverge even though the rod does not make contact. If the rod is removed, the leaves collapse again. What's going on here? Well, let's apply some of the theory we've learned so far. We can visualize the electrical condition of the rod and the electroscope by showing a representative sample of the charges. Since the electroscope is metal, electrons can move with relative ease within it. If, as a result of their random motion, some electrons come close to each other, the repulsive forces that they exert on each other ensure that they will very quickly move apart again. When a positively charged rod moves towards the knob, the charges interact. The electrons in the electroscope will try to move towards the rod. And as they do so, will flow out of the metal leaves, making the leaves positive. As a result, the leaves repel each other and diverge. When the electrons in the electroscope move towards the rod, they get closer to each other and repel each other more strongly. So, for each electron on the knob, the attractive force of the positively charged rod is balanced, both by the repulsive force of the other electrons near it and the attraction of the positively charged leaves. If we look at the electroscope as a whole, we find that the top is negatively charged and the bottom is positively charged. Since no charge has been transferred, the electroscope as a whole is still neutral. It has, however, experienced induced charge separation. If the positively charged rod is removed, the electrons will no longer remain concentrated in the knob, but spread out uniformly throughout the electroscope. As a result, the electroscope no longer has induced separation. Let's bring the rod close to the electroscope again. This time we'll ground the electroscope while the positively charged rod is held nearby. Remember that the electrons in the electroscope are attracted by the positive charge on the rod. The positively charged leaves are also attracting electrons. The ground allows electrons to enter from the earth. As a result, the leaves of the electroscope become neutral and collapse. If we remove the ground and then the rod, look what happens. The repulsion of the excess electrons will cause them to move as far away from each other as possible. The leaves which are now negatively charged diverge. Because electrons entered the electroscope when it was grounded, it now has an overall negative charge. Surprised? We succeeded in charging an electroscope negatively using a positively charged rod and a ground. Watch this sequence. Did you notice that throughout the entire sequence, there was no exchange of charge between the rod and the electroscope? We call this process charging by induction. It occurs when a charged object is used to charge a neutral one without discharging itself. Since there was no exchange of charge between the rod and the electroscope, the rod can be used to charge any number of electroscopes. Each electroscope will acquire a charge opposite to that of the rod. Charging by induction often occurs in nature. Thunderclouds frequently have a strong negative charge, which repels the electrons in the earth below. The result is an induced positive charge on the ground immediately beneath the cloud. If the charge difference between the cloud and the ground becomes great enough, a massive flow of charge results. Some people actually call it lightning and thunder. Benjamin Franklin was the first to demonstrate that lightning is an electrical discharge. He flew a kite in a thunderstorm. When he attached a key to the kite string, the sparks that jumped from the key to his hand showed that the clouds carried an electrical charge that was being conducted by the kite string.
You really think so? Of course.
In the next program, we will investigate this flow of charge. By flying a kite in a thunderstorm, Benjamin Franklin was able to demonstrate that clouds carry an electrostatic charge. The fine wire connected to the kite conducted electrons to Franklin below. Franklin hypothesized that the charge moving through the conductor was positive. Electrons had not yet been discovered. If we were to repeat his experiment, but create a gap in the wire and insert a light bulb in that gap, the bulb would light up briefly as charge flows from the cloud along the wire to the ground. As a source of continuous charge flow, clouds are not only unreliable, they're dangerous. Therefore, safer, more reliable sources must be used. Suppose instead we use two metal spheres, which are oppositely charged. If we connect them with a conductor and attach a charge flow indicator, we can see that there is a momentary flow of charge, or current. The current produced by connecting two charged spheres might even light up a light bulb for an instant. But as soon as the spheres are neutralized, nothing further would happen. For a continuous flow of charge, we need a source like a flashlight battery. A chemical reaction inside the battery, or dry cell, is its secret to success. This reaction causes the outside zinc layer to become negatively charged, and it causes the graphite rod in the middle to acquire a positive charge. We call these two charged parts electrodes. If we use a conducting wire to connect the negative zinc electrode to the positive graphite electrode, electrons will flow from the zinc to the graphite. As electrons are removed from the zinc by the conductor, the chemical reaction inside the cell transfers more electrons to the zinc. Similarly, at the graphite rod, the chemical reaction constantly removes electrons from the rod. Thus, it is possible to create and sustain a flow of charge for a long period of time. Current electricity is the name given to this continuous flow of charge. Normally, the negative electrode is not connected directly to the positive electrode. A device to utilize the current, such as a light bulb, is connected to the wire as well. The flow of charge through the bulb causes it to light up. What you see here is a simple circuit. A circuit is a complete path or loop around which electrical charge flows continuously. It consists of a source of electrical energy, a battery in this case, a conductor such as these connecting wires, and a load such as a light bulb, which uses the energy provided by the source. If a gap is introduced at any point in the circuit, the flow of charge stops immediately. As the charge flows from the cell, the chemical energy inside the cell is transformed into electrical energy. The light bulb, in turn, transforms electrical energy into light and heat. This circuit is said to illustrate direct current because the electrons continually flow in the same direction. The electricity supplied to your home is not direct current. If we could observe the electrons in the wire, we would see them vibrating back and forth. Alternating current is what we call this flow of charge, because the electrons periodically change direction. In this program, however, you will see only direct current circuits. The dry cell is not the only source of direct current. The solar cell converts light energy to electricity, and the thermocouple converts heat energy to electricity. In each case, there is a negative electrode and a positive electrode. We use this symbol to represent a direct current source, such as a single cell. A circuit in which a light bulb is connected to a single cell would look like this. How does a light bulb utilize the flow of charge? Perhaps you think it consumes electrons. Well, that wouldn't be correct. The wire functions like a pipe full of water. If 1 cupful of water is added at one end, 1 cupful of water will run out the other end. Similarly, for each electron that enters the bulb, an electron is forced out the other end. Since there is only one path in this circuit, the number of electrons passing a specific point X in the circuit within a specific interval of time must equal the number of electrons passing point Y within the same period of time. The word current is used to denote this rate of charge flow. it is given the symbol I and is an important characteristic of a circuit. In the modern metric system, the unit for current is defined in terms of the magnetic field it produces. In this program, however, we will define the unit for current in a more traditional way that is easier to visualize. Current is defined as the amount of charge that passes a specific point divided by the time it takes to do so. This equation is usually abbreviated to look like this. But how do we express the amount of charge? Well, we might try to count the number of electrons that pass a specific point in a specific time. But electrons are so tiny that incredibly large numbers of them pass a given point in a short time. Counting electrons would be as ridiculous as trying to buy sugar by the grain. For this reason, instead of considering individual electrons, we consider groups of electrons, which we call coulombs. 1 coulomb is equal to a group containing 6.25 times 10 to the power of 18 electrons. It's difficult to visualize a group of electrons, so instead, let's have this critter represent 1 coulomb of charge. And instead of picturing our circuit like this, we can visualize it like this. Now we can calculate current by dividing the charge in coulombs by the time in seconds. Coulombs per second are called amperes. If in our circuit 5 coulombs pass by point X in 2 seconds, we can calculate the current by dividing the charge of 5 coulombs by the time 2 seconds to give us 2.5 amperes. Perhaps now we have enough information to help our stranded parachutist. The reason he isn't getting the shock is that he isn't part of a complete circuit. If the situation changes, he'll soon be in big trouble. Inside every battery or dry cell, it is the chemical reaction that provides energy to produce a charge separation. If the 2 electrodes are then connected with a conductor and a bulb, the result is a simple electric circuit in which a flow of electrons occurs. The chemical energy stored in the dry cell is transformed into heat and light. We can also represent the dry cell like this. The electrical charge flows past a specific point in the circuit at a particular rate. This is called current and is measured in amperes. Since electrons are so very small, charge is measured in coulombs. A single coulomb of negative charge consists of 6.25 times 10 to the power of 18 electrons. When 1 coulomb of charge passes a specific point in the circuit, each second, the current is 1 ampere. Current, however, isn't the only important characteristic of a circuit. You can see that the current flowing through both bulbs is the same. Yet one bulb is glowing more brightly than the other. That means that in the circuit with the brighter bulb, each coulomb of charge must transfer more energy to the bulb compared to a coulomb in the circuit with the dimmer bulb. To understand how this is possible, let's consider a comparison. Suppose a lone skier allows the lift to convey him to the top of the slope. In doing so, he acquires what we call gravitational potential energy. But what if he makes a wrong turn and ends falling off the edge of a cliff? When the skier leaves the edge of the cliff, the gravitational potential energy he gained in rising to the top is converted to kinetic energy as he falls to the snow below. The skier himself doesn't change as this energy transformation occurs. In actual fact, the gravitational potential energy we have assigned to him is made possible by his position relative to the Earth beneath. If the Earth were to disappear, he would not have that gravitational potential energy and would therefore not have to worry about falling. But the Earth doesn't disappear. So, what about the end of the fall? What has happened to the energy? The energy has been used to do work to compact the snow in the drift. Now, suppose that instead of a single skier, there are a number of skiers. As it was before, as each individual skier moves up the slope, he gains gravitational potential energy. This time, however, each skier comes down more sensibly. The gravitational potential energy is only partly transferred to kinetic energy. Most of the potential energy is depleted to do the work of throwing aside the snow. As we watch this cycle, we can see that energy is being transferred from the ski lift motor to the skiers, who in turn transfer it to the snow. Now we can view an electrical circuit in the same way. Instead of a ski lift, we have a source of electrical current, such as a dry cell. Instead of a slope, let's use a length of heating element from a device like a toaster, connected to the dry cell by wires. Instead of skiers, we have coulombs of charge that are going around the circuit. Just as a ski lift gives each skier gravitational potential energy, the chemical energy in the cell gives each coulomb of charge some electrical potential energy. The gravitational potential energy of the skiers was used up moving snow down the slope. As the charge flows through the heating element, the electrical potential energy is converted to heat. At the top and bottom of the slope, a skier may often glide without losing potential energy. Similarly, the connecting wires are chosen to allow coulombs of charge to pass through, with little loss of electrical potential energy. Now, consider 1 coulomb of charge. The amount of electrical potential energy this coulomb loses as it flows through the element from A to B is significant. The potential difference is the amount of potential energy lost by each coulomb of charge between A and B, often stated as the potential difference across AB. Potential difference is measured in volts and is given the symbol V. Potential difference is equal to the energy in joules transferred by each coulomb of charge. Suppose in this example we find that 3 coulombs of charge flowing through the heating element cause the element to give off 4.5 joules of heat energy. We can calculate the potential difference between A and B using our equation. So, in this circuit, each coulomb of charge loses 1.5 joules of energy as it flows from A to B. Since potential difference is measured in volts, we can say that the potential difference across AB is 1.5 volts. The potential difference in volts can be measured between any 2 points, such as these, or these. If the wires DA and CB are good conductors, there is no potential difference between D and A or C and B. Just as skiers return to the ski toe to increase their gravitational potential energy, the charge returns to the dry cell and increases its electrical potential energy. Each coulomb, which lost 1.5 joules of energy in flowing through the heating element, will gain 1.5 joules of energy as it flows through the dry cell. The potential difference across the dry cell is also 1.5 volts. Although here it is an increase in potential compared to a decrease in potential across the heating element. Recall those two circuits we saw earlier? The rate of charge flow through the two circuits was the same. But the potential difference across the bright bulb was higher. Why does the one bulb require a higher potential difference to produce the same current flow? It must have something to do with the nature of the bulb itself, and we'll investigate this property in the next program. What exactly is an electric circuit? A heating element connected to an electrochemical cell is one type of simple electric circuit. The chemical energy provided by the cell is transported to the heating element, where it is transformed into light and heat. This transformation is carried out by the electrons as they flow from the negatively charged electrode to the heating element and back to the positive electrode of the cell. In a circuit, incredibly large numbers of electrons will pass a specific point in a few seconds. It is therefore simpler to visualize charge in units called coulombs. 1 coulomb of negative charge is equivalent to 6.25 times 10 to the power of 18 electrons. An important characteristic of an electrical circuit is the rate at which the charge flows through it. The rate of charge flow is called current and is measured in amperes. A current of 1 ampere means that 1 coulomb of charge passes a specific point each second. Another concept that helps us describe a circuit is potential difference. The potential difference between any 2 points in a circuit is measured in volts. It is simply the number of joules of energy per coulomb that is changed to some other form of energy as the charge flows from one point to another. We could, for example, measure the potential difference across the heating element And note that it's 1.5 volts. This means that as 1 coulomb of charge flows from one end of the element to the other, it gives up 1.5 joules of energy. The potential difference between the 2 points is simply the number of joules transformed as the charge flows from one point to another, divided by the number of coulombs of charge involved. To complete our understanding of a simple circuit, we need to consider one more factor. Have you ever wondered why the metal making up the heating element gets hot, while the connecting wires stay cool? The secret lies in the fact that the connecting wires are much better conductors than the heating element. The heating element is a conductor, but not a very good one, and is therefore referred to as a resistor. It's represented like this in the circuit diagram. But just how does a resistor differ from a conductor? Let's examine the difference at the atomic level. A resistor will consist of a network of atoms. If the resistor is made of the alloy nichrome, there will be 3 metals present: nickel, chromium, and iron. The arrangement of atoms is similar to that of copper, which we examined in a previous program. We visualized a conductor, like copper, as a network of positively charged ions, which can vibrate but not move about freely. Within this network, there are loosely held electrons, which can drift about with relative ease. In the case of nichrome, the structure is similar. There are, however, fewer loosely held electrons, because the electrons of some atoms are involved in bonds with different atoms. In a conductor, a very small potential difference placed across the ends of the metal will cause a significant flow of electrons from the negative to the positive end. In nichrome, there are fewer loose electrons, and the bonds restrict the number of pathways for these electrons to flow. As a result, a greater potential difference is required to get the charge to flow. Also, the moving electrons collide with ions, causing them to vibrate. Although we can't see that vibration with our eyes, atomic theory tells us that the increased vibration at the atomic level will result in an increase in the temperature of the material. Even a good conductor like copper will begin to heat up if the current is increased substantially. But in most circuits, copper does not act as a resistor, but as a conductor. When we measure the potential difference across any copper connecting wire, we will find that it is very close to zero. Very little energy is transferred to the wires. As a result, the potential difference across the resistor is almost identical to the reading across the battery. Almost all of the transformation from electrical energy to heat and light occurs in the resistor. The resistance of the resistor is defined in terms of the current passing through it and the potential difference across it. By adding more cells, we can change the potential difference across the resistor. Note, when this is done, the current flowing through the resistor is also increased. If we record the potential difference and the current through the resistor, each time we change the number of cells, we find that a straight line results. Taking the increase in potential difference anywhere along this line and dividing it by the corresponding increase in current, we'll always calculate the same value in volts per ampere. A volt per ampere is called an ohm, often shown like this, So our heating element is a 15-ohm resistor. The resistance of a resistor is a special characteristic that doesn't change when it's placed in another circuit. To get a current of 1 ampere to flow through a 15-ohm resistor will take a potential difference of 15 volts. In a circuit with a potential difference of only 1.5 volts, the current will be 0.1 amperes. With this background, let's have another look at our parachutist on the power line. Since the material making up the wire is a good conductor, the potential difference across the short length of wire will be very small. A low potential difference between the two hands is not enough to overcome the higher resistance in the pathway through the body. So, there is very little current flow through the body, and he feels no shock. When he touches the tower, however, there is a very high potential difference across a portion of his body. That is enough to allow a substantial current to flow. The message for all of us: never allow a high potential difference between two parts of your body. That will allow a current to flow through you, the resistor. It doesn't take much. As little as 0.01 amps can cause convulsions, and 0.1 amps, death. With a little knowledge of electricity, we can all keep jumping.